We conclude this chapter with a summary, really, a discussion of the simulations we've just gone through in the previous two sections to wrap things up and to give some advice, some intuition based on what we've learned. We've seen a few important properties of these four methods. One of them is that noise on the state of charge estimates really must be considered in order to estimate the battery total capacity well, properly. Even using a sigma of 1%, which is very optimistic, we see that noise is a consideration. If your SOC estimator is not that good, then the noise will even be a bigger consideration. We found that least squares methods, weighted least squares methods, other methods really simply fail. They give estimates that are in the ballpark, but we looked at the estimation error bounds and they were awful. They were way too optimistic, and the estimates in most cases were biased. So the biased estimate, unreliable bounds, just don't use them. This here is a big warning. We looked at the goodness of fit, and the goodness of fit said, no, stay away, danger, danger. Methods related to total least squares, however, where we do consider noises on the SOC estimate, are required, and they do give reliable total capacity estimates. In principle, we said that the weighted total least squares method, which was non-recursive, remember that one, is going to give the best results because it takes into account the most general of the cases. But we've seen in practice that the total least squares and the approximate weighted total least squares methods can actually give better results in practice because we can initialize them. They have a recursive form. The weighted total least squares is non-recursive, so at the first data point, it only has the first data point to work with. It doesn't have the kind of nominal capacity from the factory to work with as the other methods do. And since these two methods, the total least squares and approximate weighted total least squares methods, give nice recursive solutions, we should always choose one of them instead of the weighted total least squares. There's really no reason to use the weighted total least squares. So out of all of our methods, we've now thrown away least squares, or weighted least squares. We've thrown away that one, and we've thrown away this one, and we've kept, to date, those two methods. If in our situation the measurement update interval MI is constant, and we can guarantee that the sigma xi is proportional to the sigma yi for all measurements, then these two methods give identical results. So those are the only two things we're still considering, and they both are the same. The TLS method is simpler, so use it. AWTLS is more complicated. No need to use it. But we found that if the measurement interval is not constant, like in a plug-in vehicle of any kind, then the AWTLS method gives better results than TLS, and sometimes TLS fails. And that word sometimes makes me worried. If it fails sometimes, can I be sure that it's going to work in whatever situation that I happen to use it next? And that makes me think I probably shouldn't use it at all unless I'm guaranteed that the measurement update is constant. So this sometimes fails is especially important in any kind of a plug-in application when updates are done when charging the battery. And the reason for doing that, remember, is that we have a big improvement on the total capacity estimate because we know one of our SOC values exactly when we cut in half our sigma xi. The AWTLS always, in our simulations, gives results that are at least as good as the other methods. The only reason not to use AWTLS is that it's more complex than some of the methods, really all of the methods except for the weighted total least squares method, which is not recursively computable at all. In the simulations we've done, we've said that the noises that contribute to sigma yi are current sensor errors only. In practice, these are gain errors and bias errors and noise errors and nonlinear errors, and all that we've chosen to consider are noise errors. So if you think that the other errors are a factor, then add them to the simulation and see what happens. The gain errors and nonlinear errors are going to bias all of the methods, but we think that the biased values of total capacity that you get are actually going to be consistent with computing energy and power because the same sensor is used to estimate capacity as it is to estimate everything else. So we think that it's going to cancel out, is our guess, although I don't know that for certain. A bias error in a plug-in situation can be at least mostly corrected for if we assume that the coulombic efficiency of the cells is about equal to 1, which isn't too bad. Then whatever discharge ampere hours I get and whatever charge ampere hours I get, those should put me at the same point, right? And if I have a bias error, they won't. It will seem to do something like this if I'm biased in the discharge direction, or something like this if I'm biased in the charge direction. So I can actually compute a very good estimate of the bias by counting discharge ampere hours and charge ampere hours and setting them equal to each other, solving for the bias, and then correcting for what this point actually is based on that. The output error bounds on our total capacity estimate, even with the optimum estimator, are larger than you might have expected. If you go and look at some of those pictures, you say, wow, there's still some uncertainty, quite a bit of uncertainty in what the true capacity is. And so this really underscores the need for a method that doesn't predict only the capacity estimate, but it also predicts the error bounds. Because these error bounds, I mean, they're not exaggerated. They're based on all of the math that we've developed here. And it says that even the best methods, while they give you an estimate, there's some uncertainty about how good that estimate is. If we don't take that into account, the user has no idea of how good or bad the estimate happens to be. So if it says it's 10 amp hours capacity, well, that's great. If it says that it's 10 amp hours plus or minus 0.01 amp hours, you say, oh, okay, now I'm really confident that it's 10. Otherwise, I don't really know. It might be around 10, but I don't know how close that is. And this is really important. The capacity estimate of a cell by itself is not terribly useful. The reason, remember, going all the way back to chapter 1, why do we even want to know capacity? Because we want to know energy. We have energy equals capacity times integral of OCV over the range of OCV that's used. If my estimate of capacity is wrong, my estimate of energy is going to be wrong too. So my energy estimate might be overly optimistic, which means I'm going to run out of charge and pull over on the side of the road before I get to my destination. Or it could be overly pessimistic, which means that I get really worried if I'm going to make it to my destination or not, when in fact I shouldn't be worried at all. I'll make it just fine. Neither one of these is acceptable. So I need to have, however you do it, whether you use this method or use some other method, I urge you to use a method that produces error bounds as well as the estimate. That brings us to the end of this chapter. You'll notice if you flip through the next few pages that there's quite a long appendix where I give tables for the Kalman filter-based methods, and I give some code for these last methods based on the total least squares methods, so you can run the code and repeat the examples. But we're going to skip over that in the formal lecture videos, and we're going to go on to our next topic. We've looked at state estimation, chapter 3. We've looked at health estimation, chapter 4. These are the fundamental estimation problems, the kind of most fundamental physical quantities that we can estimate in a battery management system. And we know that we can take these estimates and put them into a computation to determine energy and power. In Chapter 1, we saw how to do energy for a cell and for a battery pack. This one here is for a cell. For a battery pack, it was similar but a little different. And we've also seen at least one way to estimate cell power and battery pack power. We're going to look at more advanced methods to do that in an upcoming chapter. Before we do that, we're going to take a little bit of a break from some of the math for a little bit, and we're going to look at an important issue of balancing or equalizing cells in a battery pack. This is in many ways an electronics problem, but it's also an algorithm problem because we have to make some design decisions as to what is our balancing criteria and how quickly do we want to do it and things like that. So that's what we look at next.